For the second part of this early morning session, we have Dana Fisman here. She, I think, might share the award with others in the room for longest travel here, but I'm super happy that she took all the efforts to come here. And Dana has done incredible work on active automata learning. There's so much inspiration you can get from that work. And then she's also done a lot on syntax guided synthesis. And today, as I see, she will talk about something slightly different that I'm very much looking forward to.
Thank you for the introduction. So I have two disclaimers before I start. So first, I'm not sure how much this talk is kind of falls under the official title of the workshop. But having said that, the topics of edit distance and robustness came up a lot during this week. So I hope you will find it relevant. The second disclaimer is that I'm going to talk about, a lot about edit distance, but this is not really my field of expertise. I just stumbled upon some questions and I find it interesting, and I hope that you would too. Very important. So this is a joint work with Joshua Groging, Oded Margalit, Elina Sudit, Eli Tsarfati, and Gervais. So a couple of. All right, so my main goals when I studied this subject, so the first one was that I wanted to have an edit distance between infinite words, and I'm going to explain in a few slides why I think this was an important question. The other one, completely unrelated, or not completely, but came from a very different direction. I wanted to distill what I call the natural robustness that hides in a temporal specification. So this is also something that came up a lot here, that a temporal specification kind of is a binary classification of the words into satisfying and dissatisfying. And sometimes you need a much finer classification, and I wanted to find a finer classification that captures robustness. So while these are my motivations, I'm going to speak a lot about a normalized edit distance for finite words. And we're going to discuss it with uniform weights and with non-uniform weights. I'm going to spend quite some time on this. Okay, so I'm a formal method person, and this is how I came to this problem. So in verification, as Sanjit introduced, we are interested in the question whether a system satisfies the specification. And this question basically reduces to a language containment question, which we solve using automata techniques. So the language containment question is whether the set of all possible computations is subsumed by the set of all allowed computations, as the specification defines it. So here in this case, it doesn't. And what this means is that all these computations that are here not subsumed by the specification, these are bugs. In this scenario where all the computations of the systems are subsumed by the specification, then we have no bugs. So this is really great. And now we have these two systems, none of which has bugs, and we want to answer which system is better. So just to have a practical example, so I have a specification of an autonomous car, saying that the car should stay within the lane. And I have two cars and both satisfies the specification. And I want to ask which one is better. And I think you would agree that the yellow one is better, well, because it seems that it's more resilient to disturbances, right? If we look at robustness in this lens, right? So robustness, we see it as the ability to refrain from violating the spec, even in the presence of disturbances, right? So Affiliate and et al. Looked at this problem and tried to define it in formal languages lens. And they said, okay, so let's look what are the violations of the specification, so that if the rectangle is all the words we have, then the purple part is the violations of the specification. And then robustness, what it means is basically you have to look for the kind of closest, so you have to look for a computation of the system that is okay, it satisfies the specification, but you need a very few number of disturbances to make it suddenly violate the specification, kind of. So this would be this arrow in this. Right? So mathematically, this would be exactly this formula, assuming I have a notion of distance between words. and figure that I'll solve this problem for finite words. And I say, oh, well, we are working with reactive systems. In reactive systems, we model things using infinite words. So for this reason, I need to have a notion of distance between infinite words. Yes?
There's in these words, there's inputs and outputs, right? So are you going to think about input-output robustness, or are you defining it in a way that's agnostic to that?
I'm not going to differentiate.
You're not going to differentiate. I see. Yeah. Because then it does make a difference, right?
I agree. I totally agree. So this is something to think about it further, right? Okay. So I have these two words, and I kind of want to look in how many words they are similar, and not similar, and somehow quantify, right? And the question is how to quantify it. So if we had finite words, and many of us use the Levenshtein distance, which I'm going to call ED for eddy distance. And the question is, how do I enhance it to infinite words? That was the question that. Yeah. Okay, so so what I wanted is a definition of an eddy distance between infinite words. I'm going to call it omega ed for now. And once I have such a definition, then I want to be able to have an algorithm that computes the distance between two words. And once I have an algorithm computing the distance between two words, I want to compute the distance between two languages using this definition of figurative.
So really what you want to compute is the previous infimum value of...
Exactly, yeah, right here. But let's start with finite words, so everyone is with me on the same page. All right, so eddy distance on finite words. Okay, so what's the Levenshtein distance? It basically asks how you can transform one word to another word, while what you have in your disposal are 4 types of operations. You can delete a letter, which I'm gonna use using X for the shortcut type keyboard. You can insert a letter. You can do substitution, substitute one letter with another, or you can do nothing, okay? So in this example, I can do the following. So this is, oh, oops. Okay, so I delete the first letter. So this is an X. I do no op, and then I insert here a P. I do no op. I do substitution of D with the G, and then I delete another X. And this way I get from the first word to the second word. Okay, okay. So then we have to give weight for these operations. So if we are working with uniform weights, then all the operation but no op cost 1, no op cost nothing. And then I would sum the costs and I would get 4. I would sum the weights, let's call them the weight, and I would get 4. Okay. And so the Levenshtein distance, it asks for what is the minimal weight of edit operations that we need to transform the original word to the second one. Okay? Because you can do it in various different ways, right? This is just one example. I'm gonna, so right now I'm using only weight. There is no cost. Okay, weight. Okay. So one thing to notice about the Levenshtein distance is the following. So I have these 2 words. These are the 2 words. Oh, not the 2 words, but 2 words for which the distance is 4. And these are other two words for which the distance is also 4, right? And this is a little bit counterintuitive because I think you would agree that these 2 words are much more similar to one another, right? You have only 4 letters out of 100 that are different. Here you have most of the letters but 1, right? So we want some kind of normalized eddy distance. So the question is then, how do you normalize the eddy distance? And you can think about, so if both words are of the same length, then just divide by the length of the words, right? But the words need not be of the same length. They can be of various different, right? So then it's not clear what are you going to divide with, right? So you can think about dividing by the sum or dividing by the length, the maximum of the length or the minimum of the length and so on. And the problem with all of these approaches is that they do not satisfy the triangular inequality. It's not difficult to come up with examples. just if you want a little riddle here. Okay, so just to remind everyone what we mean by a metric. So, whoops. The distance between two elements is 0 if and only if they are different. They are the same. We have symmetry, and then we have the triangle. Okay. So Marzal and Vidal, which were aware of the problem that I just mentioned of normalizing, suggested to normalize by using the path lengths. So I mean the edit path lengths, right? The letters that we use to encode the path. Okay, so now I call this the cost. So what I call the cost is the weight of an edit path divided by the length of the edit path. And they are looking for a way to have, so they're asking, what is the path, the edit path for which the cost would be minimal? Okay. So let's look at these words. So this is one edit path that transforms the first word to the second. So I substitute A with a B, I do no op, and I substitute B with an A and another B with an A, and the cost here would be 3 out of 4. This is another edit path. In this edit path, what I do is I insert a B. I do no op. I do a substitution of a B with an A, and then I delete the B. And this is a 3 out of 5. So this is better. Okay. This is better. Okay, great. So if we look at our motivating example of at least the problem with NED, with edit distance, then here we would get some what we expect, right? 4 out of 5, 4 out of 100. Right? Very satisfying. Okay, so the question is then, is this a metric, right? So if you think about the non-uniform case, right? If I give you the weights of substitution, which is not 1, so substituting an A for a B is a third, and an A for a C is a quarter, and so on, then it's not too difficult to come up with an example showing that it's not going to be a metric. Okay, but then is the question, if you work in this ideal scenario where the weights are uniform, is it then a metric, right? So we were expecting to find this a theorem saying this is a metric in Marzal and Vidal's paper, but we didn't find. Instead, we found the following. So after they showed it for arbitrary weights, this is not the case, then they say, okay, fortunately enough, practical situations are generally less contrived, and as we will be discussed in section 5, triangular behavior has actually been observed in practice for the correctly normalized edit distance. So I guess a lot of people are happy, and a lot of communities working with edit distance are happy with this empirical evidence. I'm a formal method person, so I'm less happy. I need some proof. Okay, so we found some other papers discussing normalized edit distance. And they actually both proposed another way to normalize an edit distance between words. The first one we call the generalized edit distance, or GED, and the second one, the contextual edit distance, or CED. And then we wanted to see what they say, whether the original one is a metric or not. And we find in the third one this thing that the authors of NED have shown that this distance is not a metric in the general case, but it is still unclear if it is the case when the costs are 1. Yeah.
Sorry, yeah.
Mm-hmm.
When I asked that, I think I need the mic. Sorry. So engaged.
Yes. No, when I asked about the cost, is the computational cost. I mean, like, is it clear that these things can be computed in polynomial time? Because
so I will prove that they can.
Okay.
Okay. So I will not prove. I will mention the result.
Okay.
But I will,
okay. Because it's not obvious, no?
It's not obvious.
Yeah.
Okay. So now we had 3 options that we can use, right? There are 3 potentials, right? So we have NED, GED, CED, and another version of CED. And the first point we know is that the second and third are a metric. We don't know this about the first. So we looked at other properties, other characterization that we found plausible about a normalized edit distance. I'm not going to go into details, but NED satisfied all of them. and the other two didn't. So we were really frustrated, and we wanted to work with Ned. And so together with Oded Margalit, Joshua Grogi, and Gira Weiss, we proved that it actually is a metric. And so basically, the missing part is the triangle inequality. And the idea of the proof is quite simple. So if you give me 3 points and you give me the edit path between X and Z, and you give me the edit path between Z and Y, then I can produce an edit path between X and Y. And then it is left to show that the cost of the edit path that I composed from the two original ones is less than their sum. So this is case analysis, nothing more than that. Okay, so I mentioned this to my colleague, which is a bioinformatics person, and she very politely said that this result is of absolutely no interest to anyone in her community, because no one ever needs normalized uniform weights. So let's see what we can say about non-uniform weights. Okay, so so apparently they come up in many applications. So what I try to do in this respect with Ilya Trustworthy is answering the following question. So you give me the cost of the edit operation, right? How much it costs to replace an A with a C, to delete an A, to replace it with a B, and so on. And based on this function, I have to say whether the normalized edit distance with this function would be a metric or not. So you would assume, or at least I would assume, that if D is a metric, then net D would be a metric. But what Eli and I showed is that D being a metric is not a sufficient condition. Neither it is a necessary condition. Which is a little bit surprising, right? And we came up with this necessary and sufficient condition for net D to be a metric. And it goes like this. So this is the definition of a metric, again, just to refresh your memory. So the definition of that we have for net D is very similar, right? So we have A and C are either letters or epsilon, which is what we use to capture deletion or insertion, and B is a regular letter. So the requirements is the first one is the same as in a metric, symmetry the same as in a metric. And instead of triangle inequality, we have what we call a relaxed triangle inequality. So the distance between A and B plus the distance between B and C, it should be more than the minimum between the distance between A and C. So going directly from A to C, or going from A to C via epsilon. So this is why that's not a necessary condition that D is a metric. And the reason it's not a sufficient condition is that we need this fourth requirement, is that the cost of the weight of a insertion or deletion is at least half of the maximal weight. So if the maximal weight is 1, it's just at least half. So we call a weight function on the letters that satisfy this criteria fine. And apparently, not only in bioinformatics, you need non-uniform weights. So I work with Adar and Sandra on symbolic finite automata, which is a type of automata that works with very large alphabets or even infinite alphabets. And there we also wanted such a notion of distance between letters and distance between words, right? And so we came up with a few in what we were trying to do. So if you have, if our letters are numbered between 0 to n, then this is kind of what you would, I think everyone would suggest, and this is a fine metric. Even if you work with all the integers, so the cardinality is unbounded, Sandra suggested this metric, which turned out to be fine. And in model checking, usually the alphabet is, you have a set of atomic propositions. If the set of atomic proposition is of size k, then your alphabet is 2 to the k, where so you have a binary vector where the ith coordinate is the assignment to the ith proposition. So if you have two such letters, then it makes sense to compare them according to how many signals they disagree on their assignment. So that would be the Hamming distance between these two letters, and you can normalize it by dividing by k. And all of these examples are fine. Okay, so we solved the bits that we needed to get to the infinite word case. And now I can tell you something about this. Yes.
Fine for married people are happy with this fine. Is it that what they were looking for? This fine. This
I have to check whether I didn't get
okay.
Speaking about it, yeah. Okay. So add the distance between infinite words. Okay, so we have this definition of normalized edit distance between finite words, the minimum cost of an edit path, which we are really happy about. And the question is, how do we extend it to a notion of edit distance between infinite words? Okay, so the definition that we suggest, and I just don't have to get into too much detail, designed to get into too much detail, is taking the lim sup over increasingly large prefixes of the two infinite words. Okay? And so this is a work with Joshua Grogin and Gervais. And so just to give you a few examples, so if using this definition, the distance between A omega and AB omega would be half, as you would expect. Between A omega and AB omega, that would be a third. I think that's also what you would expect. Between B omega and AB omega, so if we apply this, right, so we get, so here we have a distance of 1, and on the next prefix, it's a half and a third and so on, so it diminishes and we get a 0, right? And you get something similar if you take a rotation of the word, right? The distance would be 0. So if you think about this part doesn't go along with the definition of a metric because you have two elements that the distance between them is 0 while they are actually different. But what we get is what's called a pseudometric, that we just demand that if it is the same, it's 0, and otherwise we don't care. So basically, we show that omega ned is a pseudometric, and you can actually use, so we prefer ned, but you can do omega jed or omega sed, right, with the other normalized edit distance, and they will also be a pseudometric, right? It's just a property of lim sup operating on a metric. So then we wanted to compute the distance between two words, and we managed to show that it can be computed in polynomial time. So this is the kind of meat of this work, yes.
How are these W1 and W2 represented then?
Yeah, that's an excellent question. So I assume they are Lasso words. So they are ultimately periodic. So you have the prefix and then something. Yeah. And then we can also compute this infimum over two languages and get the robustness distance as defined by Philip and company. Yeah, so we work with Bookey automata, non-deterministic Bookey automata, and the construction works for deterministic. So I think I'm gonna stay at this level of detail in order to get to this part that I find very exciting. Okay, so here, as I mentioned, the mission is to distill the natural robustness of the temporal specification. So there's kind of an informal, implicit claim that I'm doing here is that there is such, so an omega regular language actually induces a natural robustness preference relation. Okay, so this is my informal claim, and I'm a person of proof, so I should deliver the proof, but here I'm on the defense, and I don't know how to prove this. So what Elena, this is a work with Elena Sudit, what Elena and I did, we looked at literature on quantitative reasoning, quantitative temporal logic, and so on. And we looked at all of their examples there. There are a lot of literature about this. And so we put aside the examples that are kind of use some hard-coded weights in the input, but those that don't use any hard-coded weights, we could both agree what is more robust than others, and so did anyone that we talked to, right? So for a simple example, right, if this is a very common LTL property saying that every request is eventually granted, okay? So it could be granted within one time cycle 1 tick, or we did with 2 ticks or 5 ticks or 100 ticks. So there is actually no limit on the number of ticks that it could be granted, right? So I think you would agree with me that a word which in which the distance between request and grant, right? So there is no many ticks that elapse between the request and then being granted is more robust than one in which 1,000 ticks elapse between. Okay, so we call this omega regular robustness, and what we wanted to do is the following. So you give me an omega regular language, I do some magic, and I suddenly distill from it what we call a robustness value. So the robustness value function is a function which takes an infinite word and returns a value for it. So this is some totally ordered domain. So just to explain it from another angle, so as I mentioned before, specification languages classify all the words into 2 sets, those that satisfy and those that violate. So if I'm starting with a temporal logic, you would say it's a 2-valued semantics for temporal logic, but you can think of a multi-valued semantic of whatever logic that you're working with. And there is one particular multi-valued semantics that I want to share with you. This one is a 5-valued semantics of Tabuada and Nider, which very much inspired us in this work. So they look at, they give the following example as a motivation. So the property is always A. And if you look at these words, right? So I'm going to draw them here by coloring A's with green and B's with red, because A's are the good event and B's are the bad event, right? So here, when you look at the colors, it's quite clear that the higher you are in this list, the more robust you are. Right. So the kind of mathematical explanation that Tabuada and Nider give for this is by looking at these representative formulas. So we have always A, eventually always A, infinitely often A, eventually A, and never A, right? So you can see that they are decreasing in terms of the number of A's that they require. And then you can see that the first formula satisfies this stronger one, right? The second formula doesn't satisfy always A, but it satisfies eventually always A. The third doesn't satisfy these two, but it satisfies infinitely often A, and so on. So kind of these, whether you satisfy it or not, right, determines your place in their 5-value semantics. Yes, maybe you can take the mic.
How is it with the next operator if you have globally A implies next B?
Yeah, so their semantics is for what they call RLTL. So the syntax is the same as LTL. So you have the next operator. Okay, so they deal with it. I don't want to get into details of how they do it. So this is just a motivating example, but they deal with the next operator, definitely. Okay, so what we claim is that 5 values are not enough. Okay, so I have the same property, always A, but different formulas, right? So A5 B to the omega or A2 B to the omega. And I think you would agree that, again, the upper one is more robust, right? But if I try to apply Tabuada and Nider's 5-value semantics, then both of them are here. They satisfy eventually always A, and I have no ways to distinguish with them. But I would like to say that this one is more robust, right? Especially if you replace 5 with 5,000. So we want to distinguish these words, and just an important fact is that we also, so this is the case also in this example, right? Where these formulas fall kind of here, they satisfy eventually always A, and we want to distinguish them, just a second, even though they completely agree on the periodic part, right? So we want our refinement to consider also the non-periodic part. Yes.
So I wanted to ask, actually, if you go to previous slides, maybe even philosophical questions, and this is if you think about robustness, right? Robustness means I don't want things to go bad, it stays good, right? So in some sense, I don't know why first one would be more robust, because I know that in both formulas, things are not good. Eventually, in each of them, something bad B is happening. So as I said, like it's philosophical question more like.
Okay, yeah, so I could work with, so the same preference relation would be one that I would get for the property infinitely many A's, in which both of them satisfy infinitely many A's, but there I think you would agree with me that the first one is more robust. So maybe I should have chose the formula infinitely many A's.
Is there, so like when I imagine robustness, the cartoon that I have in my head is always like, I have my reference word, and now I'm going to send it to someone, say Sebastian. I'm going to send it over a channel, and that's going to get mutated. Where the edit distances, often we're used. In that setting, this notion of lack of memory is really important, I guess, in order to be like, well, just deleting and adding it's happening. Because otherwise, if there's any notion of state, it feels like the bottom one could be stabler, in the sense that the system is trying to attract to that, like that error always happens. Whereas the top one somehow like, there's a degenerate case, some adversary sees these bits and decides to flip them all to B from that point on. And so I'm curious if you've thought about like how this relates to these kind of almost like information theory or communication theory based assumptions.
So yeah, I think it's a very nice motivation and kind of what you would associate with robustness. But the way we came up with this, right? It's kind of, we want more A's. The more A's, the better. And this is the upper one is more robust. So you can allow more errors transforming B's to an A's in the first one without violating the spec than in the second one.
Okay.
Okay, so basically, so we said you have 2-valued semantics, we have 5-valued semantics, and what we want is an unbounded value semantics. So this is our goal. We want an unbounded value semantics that captures robustness. So just to discuss the relation to omega ned. So again, in this particular example that we looked at, always A, this is a language of one word, right? A to the omega. So then you can ask whether the robustness with respect to this language of a word is the same as the omega ned of that word with respect to this single word that is here, right? And the answer is no, because, well, as I just mentioned, I want the robustness value to be sensitive to the prefix. And I designed the omega ned to be insensitive to the prefix. So I cannot get it one from the other. Okay, so we want this robustness value function. You give it an L, you get the function robust for L that takes a word and gives you some value of how robust is this. And this value, so what we expect to happen is that if the value returned for W1 is higher than that returned for W2, then W1 is more robust than W2 with respect to the language. So this is our first requirement, and this is again kind of the requirement that I have trouble proving because W1 is more robust than W2 in the eyes of who. So this matches our intuition on all the examples that we. But there are some mathematical properties that I can define and prove. So the one relates really to Rujitsa's observation, right? That maybe this example, whoops. That I gave earlier is more conformant with infinitely many A's than with always A. Okay, so I would say kind of that they both yield similar or same preference relation, but there still is a word, right? There still is a difference because in the first only this one is accepted, and in the latter one all these three are accepted. So what we demand is that there is some satisfaction threshold, right? So if we order this, if we look at the linear order and we call 0 one of the elements, then the satisfying words are above this element, and the words that do not satisfy are below this. The other requirement that we have has to do with the complement of the language. So if this is the order of the word with respect to a certain language L, if you give me the complement of that language, I would expect the order to be reversed, right? So first, the words that do not satisfy suddenly satisfy, but also the one that was less robust is now the most robust, right? And similarly, the words that were accepting are now violating, but the one that was most robust is now the least robust. So this is what we call the duality. Okay, so this is a very rough idea of how this value looks like. So it's a triple. So again, we work with lasso words, so ultimately periodic words. So we call U the spoke of the lasso and V the period. Okay. So the first element is the acceptance bit, whether the word is accepted by the language or not. The second one is a score that we associate with the periodic part of the word. And the third part is a score that we associate with the robustness of this, with the robustness of the spoke. And they are computed slightly differently. So let me try to convey how do I define the robustness of period. So in the examples that we looked, always A and infinitely many A's, it was easy. Words with more A's are more robust. How can I lift this to the general case, right? So let's look at a few examples, right? So if my language is infinitely many A's, then more A's is better. If it's finitely many BB's, then less BB's is better. If it's both, right, then I prefer words with more AA's and less BB's. That's basically the idea. So I want to have, it would be nice if I could somehow mark the letters of the word and say whether the word is good, bad, or neutral, where when it's good, it means that it kind of contributes nicely to the robustness, and it's bad if it contributes negatively to the robustness. So for this language, if I look at the first word, so this A doesn't contribute well, this B doesn't, this C doesn't. But here, the second A, kind of closing this to two A's, is a good thing, right? And this repeats in the periodic part. Here again, the second B is a bad thing, the second B of every period, right? And in this word, this is the case, right? So for instance, in this word, which is the most interesting, in the periodic part, we have two good things and one bad thing. So how should we weigh this period? So the idea is that the period's robustness is kind of its average score, right? So what's the average score? I take the number of greens and I subtract the number of reds and I divide by the period length. So kind of, this is a weight of 1, this is a weight of -1, and what about the spoke? So let's look at infinitely many A's. So I have these two words. They have infinitely many A's. They are great, but one has more B's in the spoke than the other one, right? So I would consider the one with less more robust. So kind of here, the shorter spoke is better, right? But if I look at this word, right, I prefer the one with the longer spoke because it's a better spoke. Okay, so what we do with the spoke is basically we ask kind of okay, so basically I want to ask for each letter of the spoke, is it better than the period's average? And if it's better, then it's going to be multiplied by 1, otherwise by -1. And then I'm going to sum this up. So the formula that I get is kind of, you take the weighted value of the spoke minus the weighted value of the period, and then you multiply it by the spoke. So this is a very rough idea of the way we give the marks. We actually have 5 colors, and it's a little bit more subtle, but I don't have the time to get into this. So the main challenge is to find a way to get this marking. So I have this language, I have this word. Who's going to tell me which letter is green, which letter is red, right? So usually I say I have this language. So how do I have this language? How do I represent the language? So maybe I can use a minimal automaton for the language, and I can get this coloring from the minimal automaton from the language. So while on finite words, minimal automata are very informative and kind of tell everything you want to know. This is not the case on automata on infinite words. And you have, for a particular language, you can have different automata, both, all are minimal, but they are different. And if I try to, so I don't really have the time to explain how, but if I try to take such an automaton and kind of derive from it the coloring, then they wouldn't yield the same coloring. So this is just an example to illustrate, right? So this is for the language infinitely many ABs. So the coloring that I would get here on AB would be just one B in every period of two, one green in every period of two, but here it would be A, B, A, B. So I would get two reds and one green in a period of 4. So the question is what do we do? Okay. So actually here, this is the automaton that we would like for this example. And it's not minimal. It has actually 5 states, but it gives us that this AB loop is the best thing that you can get for this language. Yeah, and the question is, how do we get this automaton that we think reflects it better, right? So again, this is what I told you that we wanted to do. And I said, okay, you give me a language. I didn't say, how do you give me the language? So you can give me an automaton, a non-deterministic Brooke automaton, a deterministic parity automaton, whatever you want. But what's important for me is to be able to distill a robustness value that represents the language rather than the particular representation in which you gave it to me, okay? So an easy way to avoid it is if I say, okay, in what representation you give me L, you give me an oracle for L. So I don't have L representation at all, but I can just query about it. So we take an oracle for L and we construct from it what we call the robustness deterministic parity automaton for L, which is a new canonical model that we came up with. And we construct it using automata learning techniques. Okay, so the downside is this, the robustness DPA might be exponential in the size of the minimal DPA. So it's not surprising that it might be bigger because it does convey more information. It's also not surprising, at least to me, that it's exponential because there were various attempts to get a canonical representation of omega regular languages, and all of them turned out to be exponential in the size of a minimal deterministic parity. So this is kind of expected. So there are a lot of notions that we enjoy developing towards this. I think the most interesting one is the dominant suffix, which is kind of the bit of the infinite word with which we associate the last letter is a good one or another one, but I'm gonna spare you the details. So yeah, so in our, we were pleased that we kind of managed to define a robustness value function that answers all the requirements that we had. And we can construct it from an oracle for the language. And the size would be polynomial with respect to the robustness DPA, which can be exponential in terms of the original language. So that's what I wanted to share with you. So thank you for listening.
Thanks for the very interesting talk. Are there any questions?
I have many questions, but I'll just do the one for now, and then maybe follow up later. So in this duality assumption that that you gave, there is this requirement that that if you flip things over, yeah, I'll give you a second to put it back. That if I flip things over, that the most robust before now becomes the least robust.
Right.
And I was wondering, going back to apologies for going back to the channel assumption, is this kind of assuming that you have the symmetry of, like, if I were to edit one letter, it's easier, it's just as easy as editing it the other way around.
Yeah.
And so, like, if that wasn't the case, then this maybe would have to be relaxed.
Right,
or
right.
Okay. Interesting. Okay, cool. Thank you.
Other questions? And let's close the session here, and we'll reconvene 10 past 11.